Hi everybody, so I'm going to do a quick little summary of angular measurements comparing to linear measurements as just a brief overview to help bring things together. I did this in class with one of the sections and they said it was really helpful and it was insightful, so I decided to make a video of this, especially with the upcoming tests and quizzes and after we've gone over the energy and angular momentum work, and plus the dynamics before that and the kinematics before that. A lot of students still feel shaky about angular. It is more difficult and we haven't spent as much time to give you the practice, but I'm hoping when you look at this you say, okay, maybe you understand more than you realize. You just haven't seen the big picture because you've been kind of lost in the weeds and the details of everything. So let's start with what we know about linear. Okay, all the linear measurements that we've done in through the year, right? So I'm going to put linear right here. And so let's start with the basics. Position, we have velocity, we have acceleration, we have mass, then we learned about force, then we might have talked about at some point momentum and impulse, and then work, and let's say kinetic energy. I think I've hit all the major ones. So in this unit on rotation, we've learned that there is an angular counterpart for all those. So x maps into theta, angular displacement measured in radians. V maps into omega. A goes into alpha. Mass, we've learned, we spent a lot of time recently on moment of inertia. Force and torque are counterparts. Momentum and angular momentum. Impulse and impulse, so they're really the same thing, but I'm going to put a little r there for rotation. W is still W, but I'm going to put a little r there. And then Ke, there is a kinetic energy, R. Okay, so every single one on this list we've talked about at some point has a counterpart that's linear. So what is really useful about that is let's say I'm asking you, what's in some equation for angular? Let's say I want to look at angular impulse. And you, for whatever reason, don't have equations in front of you. So you can say, but I know what impulse is. I've done enough linear, and I know over on this side, impulse is F times T. Well, then the angular counterpart is simply going to be the angular counterpart to F, which we just saw is torque, and time is common to both them. So angular impulse is simply, excuse me, tau times t. So on a graph, that might be a slope or an area, but it's the same analysis you would for the linear part, which you probably felt a lot more comfortable with. Then I can take this a step further. So I know that ft gives me a change in p. So if P and L are counterparts, then I know that gives me an equivalent change in L. And if I know delta P is equivalent or can be equivalent to M delta V, then I say, all right, what's the counterpart to M? Oh, it's right here, I. And then, of course, V is an omega. So when you're looking for angular equations to relate to other things, do the same thing you would with linear. Like I said, they map exactly. Let's say we go back to kinematics, right? And I know we talked about this before, but it's reminding, a common equation in kinematics is x equals v naught t plus 1/2 at squared. So if you're looking at angular stuff, you just map this, right? So x goes to theta, v naught goes to omega naught t plus 1/2 alpha t squared. And so, again, if you can't remember or don't think you can find the angular equation, it's the exact same thing as the linear one, except for the angular counterpart. So knowing these counterparts here is really useful. Lastly, what I want us to understand is there's a bridge for every single one of these. In other words, x and theta are always related by, and all these are related more or less by the same bridge, and that's r, the radius of rotation for that particular situation. So x is theta times r, v is omega times r, a is alpha times r, I is mr squared, so it's a little bit different there. Tau is f times r, L is p times cross r, right? Where p is mv. J and j are, there's no r, w and w have no r part, and this has no r part. So if we know one, we can always know the other as long as we know r. We can go back and forth. So you have two ways of approaching these equations. You have taking the linear counterparts and just translating it to the angular ones. And if I have to go back and forth between two, I just use that R part. So that should be maybe somewhat, what's the word I want to say? Oh, what's the word? Fuck. Somewhat reassuring to you. So if you're feeling like I really don't have a good handle on equations, but you feel you have a good handle on the linear part, not the rotational, I want you to see that it's not hard to go back and forth between the two.